Alright, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So today we're going to learn a new topic for introduction to statistical programming. So this topic is a linear regression. For today we're going to look into a simple linear regression. Right, so the objective of this topic is to understand the difference between correlation and regression. Remember last lecture we already looked into a correlation method, and we're going to understand the uses of simple linear regression. I'm going to analyze simple linear regression using a proper step to know how to present a simple linear regression result and to know how to do a prediction in simple linear regression. Right, as a revision, last class we already looked into a correlation. So correlation is we measure the association between two variables, and these two variables should be a continuous quantitative, right? So but in correlation it only measure the strength of association between two continuous variables. It gives us the direction of the association, whether it's positive correlation or negative correlation between two continuous variable, and it is also useful when the both variable, dependent and independent variable, are not clearly specified. So the objective of correlation is just to measure the relationship between two continuous variable, nothing than that. So if you want to do a prediction between two continuous variable, you cannot stop at correlation. You need to proceed with linear regression. So the definition of linear regression is a statistical methodology that utilizes relation between continuous variable. So one variable can be predicted or estimated. So the y variable, which is a continuous, which is a dependent variable for simple linear regression should be continuous quantitative variable. It only can accept a continuous quantitative variable. You cannot replace it as a discrete quantitative variable. For example, the example for continuous quantitative variables such as height, weight, so it came with a range of value, right? So if you have variables such as year, number of student, number of car, that is not a continuous, it's not a continuous quantitative variable. It's actually a discrete quantitative variable, so it cannot accept others than continuous quantitative variable into a dependent variable for linear regression. For x, which is independent variable, it can accept either continuous quantitative variable, discrete quantitative variable, or categorical quantitative variable, right? So this is the example of research question. Does the amount of calorie taken associate with body weight? So this is the example research question for correlation method. It's only want to measure the association between calories and body weight. If you want to do a linear regression, another additional question should be asked: would the amount of exercise in hour predict the change of blood pressure? So this is the example of research question for linear regression. We want to know unit change in exercise hour will change the measurement in blood pressure, right? So in another example, how much 10-hour physical activity change in the weight in kilogram? So this is another example for research question for simple linear regression, right? So another example, how much will 1 gram of salt change blood pressure in Kelantan population? So we need to identify the dependent variable. The dependent variable is the outcome variable, which is a blood pressure. Blood pressure are measured in a continuous quantitative way. And predictors, which is independent variable, should be a amount of salt, right? So in linear regression, we measure the linear association between the continuous variable, and the continuous variable should be in dependent variable, right? It is useful when dependent variable and independent variable are clearly specified. It apply when a prediction in outcome variable is among the objective of the analysis lah, right? So now let's look at the term of variable that we're going to use in conducting a simple linear regression. The dependent variable, also known as outcome variable or response variable or responding variable or regression. It is a variable that researcher would like to determine or to examine if the independent variable change, right? Independent variable is a variable in X as is, right? Is also known as a predictor variable. A change of unit in independent variable would also affect the change the value in dependent variable. So for example of dependent variable and independent variable, we have blood pressure. Salt intake will affect the blood pressure. Blood pressure will depend on the salt intake. BMI would also depending on exercise frequency, and cholesterol level also depend on the fat content, right? So the uses of linear regression, right, to assess the linear association between dependent variable and independent variable, that is the main point. But this first uses of a linear regression also have in a correlation method. It also measure the same thing, right? We measure the association between dependent variable and independent variable. And the second thing that the linear regression is used is to determine the change in a value of dependent variable when independent variable change in a particular unit. To predict the value of dependent variable for a specific value of independent variable. To control the for the confounding effect of the independent variable, this is when we do a multivariable analysis lah. Right. Now let's look at the introduction to simple linear regression. Before we conducting a multiple linear regression, we should always do a simple linear regression to see the relationship between each variable, means dependent variable and independent variable. Right. Now let's look at the definition. The definition for simple linear regression: a statistical methodology that utilizes a relationship between two continuous variables, so then one variable can be predicted. So in simple linear regression, there are only one dependent variable and only one independent variable, right? So, and I would like to emphasize again, dependent variable should be a continuous quantitative variable. If you have others than that, you should not use a linear regression. It will not fit well, right? So now let's look at the assumption of a simple linear regression. So let's look at this. First assumption is the value of independent variable is fixed or non-random or mathematical variable. So this one should be done at the sampling design stage, right? So we need to identify what is the variable involved, and the variable should be collected in the same measurement. Let's say you are collecting variable height. Height should be measured in centimeter for all observation. If you want to measure in inches, it should be measured in inches for all observation. It cannot be mixed measurement value, right? The second assumption is independent variable should be measured without error, right? Means that when you do a data collection, so the measurement should be correct and accurate without error, right? So these two assumptions, the first assumption and second assumption, should be done at the sampling design stage and the data collection stage. And let's look at the third assumption. For the age value of X, the subpopulation of Y should be normally distributed. So we need to measure the normality distribution for error of the model, right? So error of the model, which is a residual value getting from observation minus predicted value. Observation minus predicted value, we will get a error. So if you still remember on the scatter diagram we draw on the last lecture, right? We have a scatter diagram, and then we're going to draw a line through the scatter diagram. So the difference between the line and the point of observation is called an error. So the error should be normally distributed. Right, the fourth assumption for a simple linear regression is the variance of the subpopulation of the dependent variable should be equal. So means that we're going to measure the variance of the predicted value and the residual value. So the variance on the residual and predicted value should be equality variance, and the mean subpopulation of dependent variable should be linear on the straight line. So this is the assumption of linearity. In order to use linear regression, we need to make sure the dependent variable is linear. So to measure linearity, we can use a scatter diagram to look into the linearity, and we can also look into a scatter diagram to look the pattern of the distribution, either it's a linear or quadratic or something else. It should be on linearity lah, because we want to use linear regression. And the last assumption is the dependent variable y has a value that's statistically independent lah. So as a conclusion for 6 assumption, I will come up with one short acronym, which is LINE. LINE means that L for linearity, I for independence, N for normality, E is equal to equal variance. So this is the summation acronym for linear regression assumption, right? So now let's look at a step in simple linear regression. First, we should always explore the data and describe the data, create or scatter plot to look the pattern and the linearity of the data. Is there any association between dependent variable and independent variable or not? If there are no independent association, then we might expect when we fit a linear regression model, there will no association at all, right? And second step is to fit a least square line. To fit a least square line, we're going to use least square method. So of course, out there are a lot of methods to fit the regression model. The first is a least square method. We have orthogonal method and so on. But in this syllabus, we only focus on least square method. And the third step is to evaluate the fitness of regression model, and then we're going to evaluate the importance of the independent variable. We're going to measure the slope, right? Whether the slope is important or not important, or better one. And we're going to do a residual diagnostic check for the assumption. We're going to check for the assumption, four more main important assumption, which is line, L for linearity, I for independence, N for normality, E is equal to equality of variance. And last, we're going to interpret the result and do a prediction. This is optional, right? Now let's move to the R software. Alright, let's continue on RStudio. So let's create a new R script. Right, so this chapter is about simple linear regression. So we're going to use dataset regression.dta. If you notice, I already put all my dataset on Google Classroom. So you can go to find my the dataset in Google Classroom. I already download my data I have here. So I need to create a working directory to my dataset. So I create here. So now let's look at I'm going to use dataset regression.dta. Right, if you look at into the folder, working directory folder, right? So we're going to find regression.dta. So extension.dta is a starter file So to import a stata file into our environment, we're going to use either Heaven library or foreign library. So I'm going to use library Heaven, right? So then I'm going to store my data into data1 object, read underscore stata, right? And then I'm going to copy the file name into read underscore stata. Oh, sorry, I have a double quote. Just copy this one. Alright. So I already load the data into my working directory, my environment. So let's look at the dimension of data1. So I have 86 observation with 4 variables. Let's look at the names of data1. We have subject, weight, fat, and RBS. So to know the label of this variable, let's look at str structure of data1. So for structure of data1, we have table, 86 observation with 4 variables. Table is also equivalent to a data frame lah. So the first variable is subject, which is numeric, right? So and then second variable is weight, is also numeric, right? The label for weight is a waist circumference in centimeter. Fat variable is a numeric variable. The label is abdominal fat thickness in centimeter. And RBS is also a numeric, is a random blood sugar, right? So the advantage of loading other statistical software dataset means that the data is already well defined, so we no need to redefine the dataset. So as you notice, weight, fat, and RBS is already in numeric file. Let's look at the head of the data. Oops. So we're going to ignore the first variable, because the first variable is just notify the subject value, right? The number of subject number 12, subject number 54, and so on. Right, we're going to use waist, fat, and RBS, and we know that fat will contribute to waist will contribute to fat, and RBS also contribute to fat. Right. Before we start, right, we're going to explore the data first. Right. Before we start, we're going to explore the data. Let's look at the summary of data1. Without the first variable. So we know that the mean of data1 weight is 91.42, mean for fat is 102, mean for RBS is 10.768, right? So now let's say I want to display all the mean and standard deviation together. Instead, we're using a dplyr package. I just need to write down the coding for very long, but I just want to use a very short package library, table 1. Right? This is table 1 library. Allow us to use a create table 1 function where it will display the mean and standard deviation together. Right, so I'm going to use create table, create table 1, right, and then data should be data1 -1. Oops. Data equal to data1. So here it will provide us, let's say I don't want the value, the first variable. Right, so here I already have the value of mean and standard deviation together. Mean for weight and is 91.42 with standard deviation 10.96. Right, so this is one way to present the data, to explore the data. Let's look at the scatter diagram. scatter diagram. This is a exploring the data set lah. Scatter diagram. Right, scatter diagram. Let's say plot fat and waves. Let's say for scatter diagram. Right, let's look at the documentation from base package. The first argument is x and followed by y. So let's say my dependent variable is fat, so I just want to put waves and fat. Right. So but before that, I'm going to attach data 1 into my R environment, and then I'm going to plot the scatter diagram. So if you look at the scatter diagram, you will see that there is a positive correlation lah. There are increasing in trend of the scatter observation, right? So we can say that waves and fat has a positive correlation, and you need to make sure where you put your variable on x-axis and y-axis. Y-axis should be always dependent variable, and x-axis should be always independent variable, right? So now look at another plot, which is plot RBS and fat. So RBS and fat also shows a positive correlation, but you notice that the correlation between RBS and fat is getting more stronger compared to waves and fat, right? So now let's look at the normality of the data. Normality. So if this normality is not part of the assumption for linear regression, right? If we just want to know the normality of the data, let's say I put a box plot for fat. So it will show us the normality function, right? Normality, the box plot for normal distribution, right? Now let's compare this graphical presentation or using box plot using another presentation. Let's say let's use QQ plot. This is a box plot. Let's use QQ plot. Right. For QQ plot, we need to use function QQ norm, right, and then put fat. So it will plot the distribution, and then we need to add a QQ line fat. So if you can see here, we are looking into fat variable. So if you're looking at the center, the data are close to the line and a bit skewed on the right hand side and upper side. So if you compare with scattered box plot, we can say that the data is normally distributed by I is normally distributed. You can see on the right hand side, on the left hand side is the area on the left hand side is a bit larger, very slightly larger compared to the upper side, but we can say that this is a normal distribution. So to confirm this one, we going to use a normality test, diagnostic test. Let's say I'm going to use Shapiro test, weak test. Let's say fat. So if you can see here, based on Shapiro weak test, it says that the p-value is less than 0.05. When the p-value is less than 0.05, it indicate that this value is not normally distributed lah. Let's compare with Anderson-Darling method. So to use Anderson-Darling method, we're going to use library not test, right? So add test fat. So same result with Anderson-Darling normality test. It also shows that the p-value is less than 0.05, means that the normality is not, for fat is not normal. But we can by graphical presentation, we can say that it's also um, slightly not normal lah, right? Slightly not normal. Let's compare with another test, which is let's say we like so much with the Lily 4 Kolmogorov-Smirnov test. Lily 4 Kolmogorov-Smirnov test. Lily 4 test is a modification of Kolmogorov-Smirnov test, right? So based on Lily 4 Kolmogorov-Smirnov, it says that the data is normally distributed, right? But for based on Anderson-Darling and Spirowick, it indicate the data is not normal. But for Kolmogorov-Smirnov Lily 4 method, it says that the data is normal distributed. So which test should be believed? Based on the paper from Professor Yap Biwa, it says that the power of Spirowick is more compared to other statistical method, statistical test for normality lah. So then we will choose Spirowick lah to indicate that the normality of the test. So that's all. This is exploration for one variable. We can continue for others, waste and RBS variable. So now I'm going to show you how to develop a simple linear regression model. So for this simple linear regression model, and you should notice that the normality check for the previous I did is not a part of the normality assumption for linear regression, right? So we need to check normality test with residual value, not individual marginal value, right? So we're going to use a simple linear regression. Let's say I'm going to model fat and waste. So I'm going to name it as model number 1. To run a linear regression, I'm going to use LM function. So let's look at the documentation for LM. So the documentation for LM, if you can see here, is a fitting a linear model. So the function LM should input the first argument, which is formula. Formula is the object class, one that can be caused to class. A symbolic description of the model be fitted. The detailed model can be given in detail lah. So now we need to add the formula. Our formula is a dependent variable equal to waste, right? So this is instead of putting equal sign, we are going to put tilde sign, so to indicate the formula. This is for simple linear regression lah. If you want to model multiple linear regression, you just need to add plus fat, right? But in this lecture, we only focus on simple linear regression. So fat, waste, right? So I just already ran the linear regression model. To look the model specification, model 1. So this is the formula, and this is the coefficient beta naught and beta 1. So the formula would be y equal to negative 266.446 plus 4.033 x. So this is the formula, regression formula. But this information is not enough to us. We're going to use summary model 1, right? So it will give us all the information that we need. So in this information, you can see the first information will state the formula that we use. Fat equal to waste. This is fat is our dependent variable and waste is our independent variable. And this is the residual value at the minimum of the value of the residual, first quarter of the residual, median, which is a second quartile of residual, and the maximum value of the residual lah. And to test the coefficient, beta slope, beta coefficient, so we're going to look into a coefficient table. So in coefficient table, they give us estimate, standard error, t value, and the probability p value lah. So this is the intercept, and we're going to look into waste. So waste, the estimated beta 1 is 4.0328. So it's actually same as the previous give lah. This is a standard error, this is a t statistics, and this is a p value. So based on the hypothesis, the hypothesis would be null hypothesis. The waste have no significant relationship with fat. So the alternative hypothesis, waste have a significant relationship with fat. So since the p-value is less than 0.05, so we're going to reject null hypothesis, we're going to accept alternative hypothesis. So alternative hypothesis say that waste has a significant relationship with fat. So now let's look at residual standard error. So this is a standard error residual, 27.26, and with 84 degree of freedom. And this is a multiple R squared. The multiple R squared is actually a R squared lah. So we have 72.69% of the variation in fat were explained by waste, and the balance were explained by other variable that not included in the model lah. Right. This is the F statistics. If you previously used SPSS to run linear regression, you will notice that there is second table will be ANOVA table. So this is the value for ANOVA table. So now what does this values tell us? The F statistic is 223.5 with 1 and 84 degree of freedom, and the p value is less than 0.05. So the hypothesis for this one is H naught. The model is not valid for prediction. H1, the model is valid for prediction. So based on F table, right, the ANOVA table, right, the p value is less than 0.05, so it indicates that the model is valid for prediction. So this is what the linear regression model tell us lah. So we can use, if you are thinking that you only want this value, right, so you can quickly look in this value, or you can use a library, Broom library. Broom, and you just simply can type tidy model 1. So it will simplify the model. Instead of reading all things that you just want to read the coefficient table, it will simplify the coefficient table for you lah. Right. So sometimes when you want to do linear regression, right, you also want the confidence interval instead of giving the p-value, right? So you just type confidence interval. Instead of typing giving the p-value information, you need to add another information such as confidence interval. So to get a confidence interval, you just type confin function and type model 1. So it will give us the confidence interval for 95%. Right. So this is a lower confidence interval, and this is the upper confidence interval lah, for this value for waste. Right. So then after we already feed the value, feed the model, we need to check for diagnostic check lah, assumption. So if you look at the this one, we already done. Fit the least square method also done. We also evaluate the regression model, evaluate the importance of independent variable, and then we want to do a diagnostic residual diagnostic test lah. So for residual diagnostic test, let's look at the assumption. Where is the assumption? Yeah, the assumption is first we need to check the normality of the residual, right? So now, normality of the residual, if you look at you want to know what are the attribute, what are others information that the model give to us to check others information provide from model 1. So you just type attributes model 1. So by typing attribute model 1, you can see that in the model 1 they give us a coefficient value, residual, effect, rank, fitted values. Fitted value is a predicted value lah. Predicted value, residual is an error, right? QR residual, degree of freedom residual, X level, quarter model, right? Now to check assumption. So first assumption is normality assumption. So we can check assumption for using residual method lah. Let's say we use box plot model 1 and core residual. So if you can see here, there are one outlier, and you can see the area on the left hand side is quite bigger compared to the area on the right hand side. So it's slightly skewed to the left distribution, but we can compare by using QQ plot model 1 right, and then a QQ line model 1. Oops, kejap ya. Oh yeah, model 1, but we need to specify residual lah. Yep. So you can see here is a bit skewed to the right, the left distribution. Kalau kita skewed to the right distribution lah. Kalau kita tengok di sini pun dia lebih kepada kanan. Right. So yang lain-lain nampak macam okay lah, but we try to confirm it with the normality diagnostic test. So let's use Shapiro-Wilk test model 1 and then click on residual. So but in Shapiro-Wilk test indicate the p-value is more than 0.05. So we can say that the normality of the residual is normal lah, right? So if you want to conduct histogram also can, don't worry. So let's say I put M1 equal to mean of model 1 residual, then run this one, std lah, std equal to sd model 1 residual, and then I'm going to create histogram model 1 residual, but I'm going to put the probability equal to true, and then density means that I'm going to make it the color lighter, right? Density equal to, let's say 10. This is just to adjust the color, right? So let's say I change to 4, we will change the density lah, right? So just to adjust the color 16, right? So then I'm going to create denorm, right? Curve. I'm going to create curve denorm x sd. So this is m1 std, right? And then I'm going to create the color should be equal to dark blue, and then I'm going to create the thickness of the line, let's say 2 lah, and then add equal to true. Right. So you can see here the data is normally distributed lah. Right. Okay. Right. Instead of this one is the first one. The second assumption is to check the linearity. Checking the linearity and equality of variance. So to check the linearity and equality of variance is we can do it into by using the same chart. So the chart that I'm going to produce is the residual versus predicted value. So residual is in y-axis and predicted value is in x-axis. So we just need to remember xp yr means in x-axis plot predicted value, y-axis plot residual value. Right. So now to do that, we just want to plot x-axis is model 1, residual predicted is fitted value, and y-axis should be residual value lah. So if you plot this one, you can see. Let me pause the video first. Let me show another slide. Right, I have another slide that shows the description of linearity and equality of variance. Right. Alright, let's look at linearity. So this is linearity. So if you see the graph pattern look like elliptical shape on the straight line, so we can say that the linearity assumption is met. If you look at the graph is looking like a quadratic or reverse quadratic, the linearity assumption is not met lah. But if you see the graph is predicted and residual value. For the equality of variance, also using the same graph, we should get the same output lah. Right, if you see the pattern is on the straight line, distributed on the straight line, so then the equality of variance are met. If you look, the data is a convergence or divergence, is the equality of variance is not met lah. So by using the scatter plot, you can see the data is on the straight line lah. So we can say that the equality of variance met, and the linearity of the assumption also met. Right. So that's how we check the normality lah. And the first one is linearity. I is independence. Independence is done in sampling design and data collection stage. N is normality. We already checked for normality, right? It's normal, and we confirm with the Shapiro-Wilk test, also normal. And E is equality of variance. We also confirm that this model is having an equality of variance, right? So now, instead of manually check the assumption, in model itself is also already provide the assumption checking, right? So just let's say checking assumption using plot model, right? You can type, let's say it will provide a 4 graph basically. So to put into one nice graph, I'm going to set par MFO, means that I'm going to plot the graph in fit the 4 graph into one chart lah. So I just type plot model 1. So it will give us the assumption checking. We can check the assumption. So you give a lot of information here. We can say that we can see the normality assumption for the residual, right? We can say that the data is normally distributed, but it's a bit skewed, but we can confirm it by using a diagnostic test, as I showed before. And then we can see the fitted value and residual. You can see the data is linear and equality of variance. And this also gives us a Lagrange Cook distance value. We can say that we can see the outlier here, but we need to do some additional tests to measure the influential statistics lah. Right, basically that's all for linear regression. Your task is remember we have another variable here, right? Variable, say name data 1. We have fed, waste and RBS. So I want you to finish up with RBS, test the linear regression with RBS, and then your task is to do a simple regression on fed and RBS, fed and waste, and do simple linear regression for PEFR, MLR, and the last one, do simple linear regression for house price dot CSV, right? Is it regression? So we have USA housing dot SAV, right? So try to do this as your practical assignment, right? So now let's look at how to present the data. So we already know, right? Summary data model 1. So how to present the data? So normally we will use Microsoft Word. Let's say this is Microsoft Word. Normally we will put in the graph lah. Let's say table 1, measuring relationship with set. So we need to put n equal to 89. So this is 89 variable, 89 observation lah. So now then we're going to create a table. Let's say I'm going to create several information. So this is a variable. This is going to be crude. So remember we are using simple linear regression, and then we're going to have what are the others value that we're going to have. Let's say 95 standard error with 95% confidence interval, and this is a p statistic and the p value, right? So let's say the first variable is waste. Crude coefficient is 4.03. Two decimal is good enough. This is 0.2627, and then confidence interval, we need to find confidence model 1. So the confidence interval should be 3.49 and then 4.57. So later on we can adjust this one first. This is going to be 50 lah. 50. The t statistic is 14.95. The p value here you can see negative negative 16. It means that if the value is too small, we're going to put at 0.001. So this is how we present. We need to put let's say this one A. This means A means for 95 percent confident interval. Right, so simple linear regression was done, all the assumptions were checked. Right, so letak kat sini, I bagi rapat sikit. Right, so this is one way to present the data lah. Right, so this is for single variable. So you don't need, if you run for let's say RBS, you don't need to create another table. You just put into this another row lah, RBS. Right, so we already noted on the footnote, this is a simple linear regression. Right, so basically this is how we present the data, and then we can do interpretation below here lah. Right, so there are another way to model to get the data in table. Let's say I'm going to use instead of we manually find the value and key in into our word, we can use another library, which is this is auto method table regression result. So we're going to use library GT summary, right? GT summary. So instead of but before we start using GT summary, we need to model the data dulu lah, model the equation, the linear regression dulu first. So I'm going to use TBL underscore regression model 1. So it will automatically fill in all the information into the table, but in this table it lack of standard error and then t statistics. We need the information lah, and most of the time instead of using include this one, we normally will also include mean and standard deviation as well. So the mean is table 1 apa tadi? Lupa dah. Table create table 1. Create table 1 data equal to data 1 minus 1. So now for waste, kita nampak tadi waste adalah 91, 42 and 10.96. Right, normally we will present like this lah. So if you are using GT summary, it will not provide all this information lah, but you can explore to add the information. There are some function that you can use to add the information lah. So instead of running by one, you can also use another function in GT summary where we can, without modeling first, let's say data 1, right, select, let's say fat, waste and RBS, and then we're going to use TBL underscore uni regression, right? So method should be adjusted to GLM, and then our dependent variable should be fat, and then p value fun should be I'm going to limit it to 2-digit style p value dot x digit equal to 2, right? And then I'm going to bold the important p value, right? And then I'm going to bold the label as well, and add global p value, right? So when I run this one, you can see here it already run a simple linear regression for all variable. If you have more than one variable, it will run simultaneously for all variable, right? So remember, I think that's all for simple linear regression. Remember, your task is to do a simple linear regression, finish up for fat and waste, fat and RBS, put into a nice table presentation. Try to do with a PFR MLR DTA and USA underscore housing .csv dataset. I think that's all. Thank you very much. Assalamualaikum.